So let's get this started. Thank you everyone to come in this earlier hour and welcome for the newcomers to the seminar series of reinforcement learning here at Imperial College London. I just realized actually that it's been 1 year since we started. And what better thing to have Jessica Hamrick today with us. She's a staff research scientist at DeepMind, and she's working on world models and ModelBased RL. That after 1 year, we haven't spoke like about one of the main families of RL. So we're going to cover this gap today. Thank you, Jessica, for joining.
Great. Thank you so much, Borja. Thank you so much for having me here to speak. I'm really excited to be here. This is actually the first external talk that I'm giving in person since the beginning of the pandemic. So it's fun to be getting up again and getting to do that. Today we're going to talk about model-based RL. Okay, so the idea of building a model and using it to make better decisions is something that's been considered for millennia, at least as early as the ancient Greeks. Even Aristotle mused about how the imagination relates to perception and decision-making, concluding that it contained elements of both, but that it was also a separate process from either. And over the centuries, imagination has continued to, well, capture the imagination. And by the 1940s, philosophers like Kenneth Craik were formulating accounts of imagination that sound an awful lot like what we think of as planning with a world model today. So he wrote, if the organism carries a small scale model of external reality and of its own possible actions within its head, it is able to try out various alternatives, conclude which is the best of them, react to future situations before they arise, utilize the knowledge of past events in dealing with the present and the future, and in every way react in a much fuller, safer, and more competent manner to the emergencies which face it. So the ideas laid forth by Aristotle and Craik have evolved to the present day, where they now play a key role in many machine learning systems. These systems are often referred to under the term model-based reinforcement learning or planning, and they've achieved very impressive results. For example, planning is a key component in systems that can beat human grandmasters at Go, solve Rubik's cubes with a robotic hand, design molecules, or pick up objects in a cluttered scene. And moreover, planning-based systems perform, as well as model-free systems, at a variety of tasks, so often with better data efficiency, including playing Atari games at superhuman level, controlling the movement of simulated avatars, solving difficult puzzle games like Sokoban, or navigating through a 3D maze. These methods are often motivated explicitly by model-based reasoning and human cognition, or at least by human-level capabilities for generalization and transfer. For example, an ability for precise and sophisticated look ahead, being able to manipulate previously unseen objects, or better generalization across states. But do these methods actually exhibit generalization to the extent that we see it in humans? And to what extent is it even the model-based part itself that supports such behaviors? It's not necessarily straightforward to answer these questions, or even to say what makes model-based RL methods work better than their model-free counterparts. And that's because model-based systems have many moving and interacting parts, which makes them difficult to build and study. So just to give a few examples, let's consider a few different families of model-based RL algorithms to demonstrate what I mean. So we could take the pure planning approach. Here we have a model of the world, and then we can use that model with a planner, for example, CEM or MCTS, or pick your favorite one. The planner then produces actions that we can execute in the world. We gather some experience, and then we use that experience to update the model, make it better, and then rinse and repeat. Already, this procedure has a ton of moving parts and choices to consider. For example, what architecture should we use for the model? What planning method should we use? What's the exploration policy? What's the choice of loss function? And this is just one of the simplest model-based methods. In fact, some people would not even really call this a model-based method, depending on who you ask. And also, like, this pure planning approach works okay for simple control settings, but it isn't really that scalable to high dimensions or long horizon tasks. To tackle those, we additionally need to learn a policy, which can guide the planner, which requires making some additional decisions about the architecture of the policy and the loss with which to train it. But additionally, just adding in a policy in this way to guide the planner isn't enough. This type of system will suffer from instabilities. I won't go into the reason for that here, but we wrote a paper on it if you're curious to understand the reason. But just to suffice to say, the solution is that we additionally need to include an additional loss term from the planner to the policy that encourages the policy to imitate what the planner is doing. This is an approach sometimes referred to as expert iteration. And another class of approaches based on DINA, which is another class of model-based methods, add yet another dimension to consider, which is that we need different data distributions for training the model and the policy. Under this approach, the model is typically trained from real experience, as in our pure planning approach, and then the policy is trained purely in imagination. And so this requires us to consider even more decisions, like should we have 2 separate exploration policies or not? And what's the schedule by which we alternate updating the model and updating the policy? So, that's just a very brief outline of a few different types of model-based systems that exist, and they all have tons and tons of components and tons of decisions to be made in them. So how do we go about understanding these? But it's important to do so. We really want to understand what are the aspects of model-based RL that drive performance. And because if we can understand that, then that allows us to innovate on new methods. So over the last few years, my colleagues and I at DeepMind have been trying to do this, trying to understand what makes model-based RL work, which of the components seem to be the most important, and then using these insights to further improve performance, especially in the context of generalization and transfer. So in this talk, I'm going to walk through some results from 3 papers that we've written, dissecting what makes model-based systems work and how we can improve them. And then at the end, I'm going to spend some time discussing the future of model-based RL, what I think is still missing from it and what we need to work on. So let's dive into the first one. We started by asking the question, what makes model-based systems work? And in particular, what's the role of deliberation or planning in these systems? And this work was done with an amazing group of collaborators, and in particular was co-led by myself and my colleague, Theo Weber, that you can see up there. So we have been focusing our analyses on mu0, which is a recent model-based system that achieves state-of-the-art performance across a various set of domains, ranging from Go to Atari. And by state-of-the-art, I mean that mu0 can far surpass human performance in all of these domains. And it's worth pointing out that mu0 incorporates many of the same components as other model-based systems, like the ones I talked about a few slides ago. So by studying how mu0 works, we can draw conclusions about classes of model-based agents in general. So let me start by giving you a quick overview of how mu0 itself works. So first, the agent gets an observation from the world, for example, the image of the game it's playing. It then uses its model of the world to plan what's the best action to take from the current scenario. The particular form of planning that mu0 uses is Monte Carlo tree search, or MCTS. And MCTS involves a few different components, not just the model, but it also involves a policy and a value. So the policy guides the search. It basically is, you can think of it as like an educated guess of like, I think this is the best action to take. So it guides the search. And then when the search encounters a new state, the value function says, this is how good I think this state is. And so by guiding the search in this way, it's able to explore a lot of different possibilities, things it could do both immediately and in the future. And ultimately, after it's done with this whole planning routine, it comes up with an action that it thinks is the best one to execute in the world that will eventually give it the most reward. So the agent chooses that action, executes it in the world, and then gets some new feedback from the world, new experience, and it can, again, do the same thing to select its next action. To learn, the agent both uses, of course, the results of its experience, but it also uses the planner. This is from a few slides ago. This is having that arrow back to the planner, to the policy. It uses the results of the planning to update its policy and value function based on the results of search. So in particular, what it does is it says, okay, after planning, like this is an updated, better policy that the planner came up with. I'm going to take my neural network policy and update it to imitate the one produced by the planner. So you can think of this as like a bootstrapping procedure. The search improves on the policy and value function, and then uses the improved policy and value function to update the neural network. So to be able to draw generalizable conclusions about the role of planning in model-based RL, we tested mu0 across a wide range of environments that varied in their branching factor, time horizon, sparsity of rewards, and variability of initial conditions. Within this setup, we asked 3 questions. First, how does planning benefit model-based RL agents? Second, within planning, what algorithmic choices, for example, regarding the planner, drive the performance of the agent? And finally, to what extent does planning improve generalization? So let's look at the first question. to answer this one, we looked at different ways of utilizing the search in mu0. So, mu0 normally does a very large tree search. I think the default is like 50 simulations, but we can mix and match that with, say, not doing any search at all or only very shallow searches in order to come up with various ablations of the agent. So the one-step model here is, this is kind of close to a model-free agent, where when we select actions, we're just drawing them from our policy from the prior, so it doesn't actually use any planning there. And then to learn, we still have to come up with a new policy for that imitation loss, but we can do that just by doing a single step forward, a single step look ahead. The learn variant uses a full search to compute that learning update, but again, still acts according to the prior. The data variant uses this sort of model-free-esque update, but then performs a full search when acting, but then when we evaluate it, we can still just draw from the prior. Learn plus data combines both of these things, so it uses a full search all the time during the training procedure, again, but then at evaluation time acts from the prior. And learn plus data plus eval, this is equivalent to vanilla mu0, the original agent, uses full search for all of these things. So what does it look like when we train these agents? So here on the x-axis, you can see each of these different agents, and on the y-axis is normalized reward averaged across the environments that we looked at. And these different colors correspond to the individual environments. So what we see with the one-step agent is that this only achieves about 50% of the full performance of mu0, indicating that using planning in some capacity is important. So we have to use it somehow, or we don't get as good results. But there's these different ways that we can use it, so which of those seem to matter? Using a deeper search to construct a learning signal gives a substantial improvement to about 68% of full performance. And similarly, using a deeper search just to act also gives improvement to about 67% of full performance. And if you look closely, actually, you can see that different environments seem to benefit more from using planning for learning versus planning for data collection. So they seem to be somewhat complementary. And indeed, if you combine them, then that boosts performance all the way up to about 90%. And then finally, remember that all of these didn't use planning to actually make decisions at test time. We can add planning on top of that, and we get a little bit more performance, reaching all the way up to mu0's full performance. So this helps a little bit, but only really in some domains, like in Acrobat and 9x9 Go was really where we only found it to help. So overall, this suggests that the primary benefit of search in most of these environments is in the learning process itself, to construct targets for the agent to learn from and to produce a useful data distribution. So moving on to question 2, we next ask which of the many algorithmic components or choices made in mu0 drive its performance. To answer this question, we looked at a variation of mu0 that introduces 2 additional hyperparameters besides the search budget. The first one is tree depth, which is where we don't expand new nodes once we reach that depth of the tree. We just use the value function to bootstrap the value and estimate from there. And so this basically controls like how deep in the tree we're planning, so how far in the future we're looking ahead. And what we find here is that in most environments, a little bit of look ahead is useful, but in most, a relatively shallow depth of 2 gives you most of the performance. This even includes games of strategic thinking like Sokoban. The only exception is 9x9 Go, which you can see here. Where it really does benefit from deeper planning, but the rest of them, not so much. For the next experiment, we change another parameter, which is this UCT depth parameter. This is the depth at which we are actually using UCT to perform the exploration-exploitation trade-off. So in MCTS, it decides sort of like which nodes to revisit versus which new ones to go to based on this technique called UCT. And so if we don't use UCT, we're basically just telling it to search, to exploit. And if we have UCT set to a very high value, then we're telling it to search very broadly. So before a particular depth, we use the UCT rule, but after that depth, we just sample from the prior. And that's a less complex form of planning. So what we find here is, surprisingly, that complex planning really isn't required in any of our environments, again, except for 9x9 Go. A depth of 1 seems to be pretty much the same as doing a deeper depth for the UCT depth. And this has an important algorithmic implication, which is that if we're just using a UCT depth of 1, that just means exploring at the root. And after that, we can just sample. And that's much easier to implement. We don't need to maintain a whole tree data structure. So, maybe we really don't need this sort of like complex planning. Finally, we investigated the low end of search budgets. And while we find that a very low number of simulations helps, a very moderate amount, say between 5 to 10 simulations, gives most of the.
Yes.
Too much search actually typically hurts performance, which is something that I'll discuss more in a few slides. Again, 9x9 Go serves as an exception, only seems to work well with a high number of simulations. So our conclusion from this is that the number of simulations seems to be the main thing that matters during planning. The other choices, such as the depth or the breadth which we're searching, don't seem to matter so much in most environments.
That's primarily a function of the branching factor of the environment, do you think, or is it?
I don't think it's the branching factor of the environment. I think it has to do with like how well the neural network is able to capture the full space of possibilities, which is, it's related to the state space and the action space size, but I think it has to do more with like the landscape of the policy and the value function. Yeah, or it's really hard to learn a good policy and a good value for it. Like these other things I think are actually, like these other games are just actually not actually as hard. And so it's harder to approximate through a neural network. I don't have like a formal, like rigorous way of saying that. I wish I did, but that's my expectation at least. Yeah. Great question. I'm going to address that question next. So. So hold on to that. Okay, so in our third question, we asked, to what extent does planning improve generalization? And the first thing that we looked at was generalization to new search budgets, so search budgets that I didn't see during training time. The intuition being that, well, presumably we can run the search for longer, use more simulations, and it should do better. But surprisingly, we see almost no improvement even using large amounts of search in most domains. So here, this is changing the amount of search that we're using at test time. And 1 corresponds to basically equal performance. Above 1 is better performance, and below 1 is worse performance. And so a common assumption as to why this might be the case, maybe we're not seeing improvements with more planning, is because the model is inaccurate, as per your questions. So we redid this experiment, but with a perfect model. And we find actually that the results largely hold. Even with a perfect model, we see only small benefits of planning at test time. And really the main exception here is Ms. Pac-Man, but we're cheating there a little bit because we're actually use like the true simulator, which includes partially observed information that a model of the world wouldn't actually have access to. For example, when the ghosts are about to become edible again after you've eaten a pill. So this is really surprising. We have a perfect model. How is it not helping in all of these other environments? What we hypothesized was that it's these other components that are part of the agent, like the policy and the value function, that might be affecting the performance here. So to test this, we combined the learned value function and the perfect environment simulator with a different type of planner, which was basically breadth first search. So we expand all of the possible actions, score them with the value function, and then pick the best one. Unlike MCTS, breadth first search doesn't have a policy prior to guide the search. It just tries all of the actions. And so we know that if it affects the performance, it's really due to the value function. And what we find is that any amount of planning hurts performance, confirming the hypothesis that it's the value function failing to generalize to these off-policy states. In other words, errors in the model of the world, the transition function, aren't the only errors we should be concerned about. In order for these systems to work synergistically, they really require good components, like all of its learned components sort of have to be good, generalizing, and working together. Just as a couple of final experiments, in the last few slides, we were looking at kind of actually a strange notion of generalization because we were still looking at the same environment. We were just saying, how does the agent generalize to new settings of its parameters? But we can actually look at the sort of more canonical notion of generalization too, which is to different environments or different tasks. So to do this, we trained mu0 on a finite collection of these mini Pac-Man mazes. So mini Pac-Man is sort of like a toy version of Ms. Pac-Man. So we trained it on a bunch of these, and then we tested it on this handcrafted maze on the right. And so what I'm going to show you is, again, as a function of the number of simulations used at test time, the performance where 1 would correspond to perfect generalization, meaning like basically doing as well on the test maze as you would if you were to train directly on it. And so what we find is that with a learned model, increasing planning only weakly improves the performance, and really only in the case of 100 training scenes, and then eventually degrades it, again, because of compounding errors in the model, clearly. But even when we use a perfect model, the results still aren't as great as we might expect. With a perfect model, planning definitely does help to some extent. So we are getting some benefit from that, but only when the number of training scenes was relatively small to begin with, and then eventually these lines start going down. So even after thousands of simulations, we're never able to achieve perfect generalization, and that's because of the errors in the value function of the policy. So the conclusion is that planning, even with a perfect model of the world, doesn't guarantee good generalization performance. So to our surprise and perhaps disappointment, planning doesn't seem to help that much with generalization, at least not as much as we would have thought, even with a perfect model of the world. So to kind of summarize all of these results that I've just shown you, I think there's 2 main things we can take away. First, planning seems to be most useful during learning and less so when making a decision at test time. As we found in most environments, planning at test time or in the moment added very little, as you can see here, even if using a perfect model, but it makes a huge contribution to the learning signal and the data to learn from. So it still can be really useful to use model-based RL, just go into it, realizing that it's going to be most useful for training, not for making a decision in the moment. This is not to say that planning is never useful when acting. Again, we did find some differences, particularly in Go. It really helps a lot. But I think it's not necessarily a given that it's going to be as helpful for this sort of online deliberative thinking. The second takeaway is that if we do want to use planning at test time, we need to have good representations for multiple different components, the policy, value function, and the model. And it's not sufficient to just have a good model of the world. In any sufficiently complex environment, we need some way of guiding the search towards regions of high reward, which is exactly what the policy and the value function do. And these need to be able to generalize just as much as the world model, or we won't be able to rely on planning to make better decisions. So this insight about good representations being important led us to our next project, which was led by Ankesh and Jacob. In this project, we investigated how to leverage better representations to improve the generalization capabilities of model-based agents. And in particular, we focused on a class of generalization problems that we refer to as procedural generalization, where the idea here is to train on a procedurally generated distribution of environments and then perform zero-shot evaluation on unseen environments from the same distribution. And we focused our experiments in particular on this environment called ProcGen from OpenAI, which consists of 16 procedurally generated games like the ones shown here. This is just 3 of them. And you can see like different procedural variations of each of the games. So when we train just vanilla mu0 on ProcGen, we find results that are somewhat similar to our previous paper. The generalization performance is limited because it doesn't have accurate enough representations. And we can see this by performing a decoding experiment where we take a trained mu0 and then we train an additional decoder from its latent representation to predict the observations. So this basically tells us how much information about the observation is captured in its latent representation of the world. And when we do that, we see that it actually discards quite a lot of information. So on the top here is the actual observation, and on the bottom is the decoding of that observation, both for 2 different games, Chaser and Climber, at time step 0 and at t+5. And the red circles basically indicate objects that are not captured at all by the reconstruction. Yellow is captured to some extent, and blue is like well reproduced. So you can see that it's only ever able to capture anything at all on the current time step, and on future time steps, it basically can't predict anything. And even on Climber, I mean, it's basically not capturing anything about the environment. So mu0 seems to miss more things than it gets right. And the reason why mu0 fails to capture this information is likely due to the particular architecture of its model, which is known as a value equivalent model. And what a value equivalent model says is basically that we're going to treat all states the same that have the same value. So it doesn't actually explicitly learn, real true environment dynamics. It just predicts transitions between different states that have different values. The way that we train this, so here you can kind of see a schematic of the architecture. So it embeds the observation, and then it predicts the policy value and reward. And then it has what's called the model, but it's, again, this like value equivalent model just predicts future policies, values, and rewards, never actually predicting any sensory observations. And the way we train this is, again, the policy imitates the search policy, like we talked about before. The value predicts the bootstrapped end step return, and the reward just predicts the observed environment reward. So we hypothesized that we could improve on this by asking mu0 to additionally predict information about the observations. And to do this, we explored 3 different self-supervised losses. So the first is perhaps the most obvious, a reconstruction loss, which is just predict the observation at a time in the future. The next is self-predictive representations, or SPR. And this is, again, another type of predictive loss, but rather than predicting the actual full sensory observation, it predicts the agent's own representations at that point in the future. And then finally, the contrastive loss, which is more of a classification problem of classifying whether its own embedding at some point in the future actually occurred at that point in time. And so all of these basically force it to consider some aspects of its observations, though the SPR and contrastive losses don't require it to fully reconstruct them. It can basically just pay attention to things that are important for predicting what's happening in the future. So we found that adding self-supervision has a huge impact on generalization performance. On the left, you can see here a comparison between, in yellow is a Q-learning baseline, in black is vanilla mu0, and in red is mu0 with the contrastive loss. And I mean, mu0 itself is not too shabby. This is already matching the previous state-of-the-art performance on ProcGen, but when we add self-supervision, it just is miles better. It learns much faster and it converges to a much higher score. And on the right here, you can see kind of how that breaks down for each game as well. So this is great. Self-supervision has a huge impact on generalization. Does it matter which version of self-supervision we use? Not really, interesting enough. So here you can again see mu0 in black. Purple is mu0 plus SPR. Red is, again, the contrastive version, and green is mu0 with the reconstruction loss. The reconstruction loss has higher variance, but sometimes does a bit better, sometimes a bit worse. Roughly, though, across our experiments, we say that they're roughly all comparable with each other. So really, as long as you're predicting something about the observations, that sort of helps to ground it, helps to anchor it, and really improves the performance. We can see this qualitatively, what this looks like. So if we come back to, these are the same qualitative results that I showed you before. And these are now, if we look at mu0 with the reconstruction loss and do the same decoding experiment, we can find that it's really able to capture the important objects in the scene in a way that it wasn't before. Again, the blue circles correspond to things that it was able to capture. Yeah. No, we would have liked to do that. I think implementation-wise, it turned out to be tricky to do, which is why we didn't do it. But that was something we always talked about doing. I wish we had done that. Good question. Yeah.
Why does adding the self-supervised loss on aspects that are labeled actually fix this problem? Because it could be that the model just consistently chooses not to represent certain things, and then doesn't have to worry about modeling its future.
I mean, yes, it could still choose to stop representing certain things. I think I'm not 100% sure, actually. This would be a good question for Ankesh, who's an expert in SPR. But my guess is it has something to do with, in particular, like at the beginning of training, like the embeddings are just random. And so it's going to capture various pieces of information, and then it has to start learning to predict what those pieces of information are. And so it ends up not just like converging towards something completely, useless. That was I guess. Yeah. Yeah, it's possible. Yeah. Okay. So I have a few more results to dissect this main result here. So self-supervision improves generalization performance. That's great. But you could say, hold on, maybe it's not actually improving generalization itself. Maybe it's just that it makes the agent train better, and therefore it does better on the test set because it did better on the training set. So to control for this hypothesis, we plotted the results in a slightly different way. So here on the x-axis, what I'm showing you is the score the agent achieves during training, and on the y-axis is the score it achieves on the test set at generalization for each point of the training curve. We're just removing the time dimension, basically. And so the unity line means that it has perfect generalization. So that would mean what it gets on the training set is equivalent to what it gets at generalization time. And indeed, if we train on all levels, so training is identical to test, we find all the curves lie on the unity line. But for smaller numbers of training levels, what we see is that mu0, which is in black, lies beneath the other versions that have the self-supervised losses, meaning that even when the agents have the same training performance, they're generalizing better. They're getting higher reward on the test scenes. So self-supervision improves generalization even when controlling for this train performance, which I thought was a really nice result. It really is. It's not just that it's training a better agent. It's not just that it gets higher training performance. It's that it actually is better at generalizing itself. Okay, so based on these results, we might ask, can we just add self-supervision into model-based agents and see their performance improve across the board? We investigated this question by varying the number of training levels used during training. And surprisingly, we found that this had quite a huge effect. Or maybe today it actually wouldn't be so surprising, but it was surprising at the time. We find that a very small number of training levels, for example, 10, results in, there's some small differences here between mu0 and the self-supervised version of mu0, but not a huge difference. But as we increase the number of training levels, we see that this gap widens. And that now, like if we train on all the levels, we see that there's a very big gap between mu0 and the self-supervised version. This, as I said, this was surprising to us. That's because we actually had previously done some experiments on mu0 with Atari, where we had added self-supervision, and it didn't seem to help the performance at all. And I think that's because Atari is a single task setting, so it lies on this side of the spectrum. So we didn't see any performance there, and that's because something about having this like procedural variation allows the model to grab onto more interesting, consistent aspects of the dynamics that it would miss in a single task setting. So the takeaway here is that self-supervision can be useful, especially when training on more environments. Okay, so to summarize the results from this second project, we found that generalization can be improved with better representations, and we can acquire those representations through self-supervised learning. However, we found that self-supervision interacts with a number of training environments and may not provide as much of an effect at all if it's used in a single task setting. So I think it's really important to be wary of drawing conclusions from the single task setting about, say, what methods may or may not work, especially if we're concerned with general agents that can generalize and transfer and so on. So in general, I think we should move away from the single task setting entirely. Okay, so let's move on to our most recent work. One issue with the previous results is that we assumed we had access to a distribution of tasks during training. But this isn't necessarily always the case. Sometimes, we might have access to the environment, but we don't necessarily know what we're going to have to do in that environment. And in those cases, we can't expect zero-shot generalization to work because, we don't necessarily have a good way of communicating reward functions to agents. So one alternative approach is that we can, given access to the environment without rewards, explore in that environment and then use model learning to capture information about that environment that hopefully then would transfer to when we are given a task, learning more rapidly in that task. So in this project, which was led by Jacob, Esther, and Yaz, we explored the extent to which model-based RL is useful for this sort of transfer. And so we're considering in particular the setting of unsupervised RL, which I sort of already said what that is, but just to be more concrete, we have an agent that's interacting with the world or the environment in a task-free manner, guided only by its own intrinsic motivation. And then the weights of this agent are transferred and fine-tuned using real rewards in a downstream task. And so given this setting, we asked 3 questions. First, is there an advantage to using model-based RL for exploration and fine-tuning? Second, what components of the model-based agent contribute to transfer performance? And third, how well do such pre-trained agents deal with distribution shift between the unsupervised phase and the fine-tuning phase? So to answer these questions, we started with the same self-supervised variant of mu0 that I talked about in the previous section. Specifically, we used the one with the SPR loss. As before, this consists of 4 components: the observation encoder, the prior heads, which predict the policy, value, and reward, a model, and then dynamics heads, which predict those quantities, but in the future, as well as the SPR predicting its own embeddings at the future states. So during the unsupervised exploration phase, we can train this agent on an environment using random network distillation as the exploration signal. Just very briefly, the way that that works is it basically computes a random embedding of the observation, and then the agent tries to predict that embedding. And then in places where it's unable to predict it are places where it hasn't seen before. And so it gets an exploration bonus from that. So, so we use this as our exploration reward, though we really could probably use any type of exploration. And then we train two variants of the model, both a model-based version, which has all of these components, and a model-free Q-learning baseline, like the ones from the previous talks that just have the observation encoder and the prior heads. Then during fine-tuning, we're able to transfer these different components to the new environment and continue training them. And due to the modular structure of the agent, we can perform these interesting crossover experiments. So we have, of course, just a standard train with model-based, and then fine-tune with model-based, train with model-free, and fine-tune with model-free. But we can also say, take the weights that were trained during the unsupervised phase by the model-free agent, and then put them into a model-based agent, reinitializing the model and the dynamics head scratch. Or similarly, take the model-based weights from the unsupervised phase and stick them into a model-free agent, throwing away the model and the dynamics heads. This allows us to disentangle the effects of, is model-based helping during the pre-training phase or the fine-tuning phase, or both? To run our experiments, we considered two environments in particular, Crafter, which you can see on the top, which is a procedurally generated open world environment survival game inspired by Minecraft, and Robodesk, which is a set of 9 robotic manipulation tasks that have consistent dynamics and randomized object locations. So it's a little bit procedural, but not super procedural. So first we looked at just how well does the exploration phase work. And what we find is that model-based pre-training leads to improved exploration on Crafter. So what we're doing here is showing the performance on each of the tasks in Crafter. It was never given the task reward, so it didn't actually, was not told to solve these tasks. This is just in the course of exploration, which tasks did it happen to do well on? And we can see that model-based in black versus model-free in red. In general, it's doing a better job at making progress on these tasks when using model-based learning. So that seems to help with exploration just on its own. And then when we combine it with model-based fine-tuning, we find that model-based pre-training yields the highest performance, which actually, I think, surpasses the current state of the art on Crafter. And this is shown in the black line on the left. That's model-based to model-based. However, if we fine-tune with model-free, so that's the this green curve. If we take the model-based agent and fine-tune it with model-free, we see quite a drop in performance that's basically like not any better than just using model-free, both for pre-training and for fine-tuning. So this drop in performance suggests that there's something in the model that it's learning that contributes to the transfer performance. On the flip side, we can alternately fine-tune the model-free agent using model-based learning, and that gives us this orange curve, which suggests that the model-free agent is also learning something useful during exploration that is not in the world model, that the model-based agent is able to pick up on and exploit during transfer. So these results combine that suggest that perhaps there's something both in the model and in the policy that are important for doing well in the transfer setting. I'll come back to this result in just a bit. But before I do that, let's talk a little bit about Robodesk, where we similarly find improved transfer performance with model-based pre-training and fine-tuning. So again, model-based to model-based is the black curve, model-free to model-based is the red curve, and from scratch is the purple curve. However, this improvement in performance is quite a bit less substantial than it is in Crafter. And we sort of ran out of time to investigate this result in too much depth, but my personal suspicion is that this might be related to the same effect that we saw in the previous paper, where the degree of procedural variation mattered. So on Crafter, again, this is a super diverse environment. Every new level that it generates is really different from other ones, so the rules are, of course, consistent. Whereas on Robodesk, the procedural variation is limited just to the position of the objects, but everything else is the same. So there's not so much diversity there. And so perhaps what we're seeing is that there's less sort of meat for the agent to latch onto, and so therefore there's less useful information for it to transfer. It's an interesting hypothesis that I think requires some more investigation. Yeah. Latent. Well, good question. You mean is it a direct embedding of the observation or the agent's embedding? I think it's the agent's embedding, actually. Yeah. Yeah, I mean, that is definitely one potential explanation for the improved exploration performance, for sure. Yeah. Yeah, I'm not 100% sure of my answer to that question, but I think it was the agent's latent space. Yeah. Okay, yeah, so not doing quite as well on transfer here. I think would be interesting to explore this further and figure out, what exactly is the difference between Robodesk and Crafter, that in one case we see really big improvements with transfer, and in other cases we don't. Okay, so while the results with Robodesk were maybe not quite as strong, it is clear that it helps in transfer. And so one question is, why is that? The other results I showed did suggest that both the model and the prior policy might be contributing to this, but we wanted to test this more explicitly. So we did an additional series of ablation experiments where we transferred only certain components of the unsupervised model-based agent to the beginning of fine-tuning. Specifically, so here, this black curve is the full agent that transfers every component, and then we can say, reinitialize the dynamics heads, then reinitialize the model, reinitialize the policy prior, and reinitialize every component except for the observation encoder. And what we see is that there's a contribution of both parts. So we see a contribution of the model that's like going from the black curve down to the blue curve, and then a fairly large contribution of the policy prior too. Going all the way down to the green curves. And so what we can take away from this is that both of these components matter for effective transfer. Again, it's not just about learning a good world model, it's also about potentially learning a good exploration policy that we can pair with that world model, and vice versa. Yeah, so the model is important for transfer, but so is the policy. Our final result concerns distribution shift. So we did some additional experiments on the meta world environment, where here we have a set of training tasks that you can see here and a set of test tasks that you can see here. So during training, again, we never actually gave it task rewards, but we allowed it to interact with all of these different training environments. And then we tried to fine tune it on these test tasks. But importantly, one thing to note is that in the test tasks, sometimes there's objects that appear that it didn't see in any of the training tasks. For example, a door close is never seen during training. So this really would require the agent to exhibit pretty strong generalization to know what to do with these novel objects. And perhaps unsurprisingly, we don't find that it provides much performance increase when we do this model-based transfer over just training the agent from scratch. We do see a little bit of, it goes up a little bit faster right at the beginning of the fine-tuning, but not by a lot, and then they pretty quickly catch up to each other. So, it doesn't seem to be quite as useful in this environment. And the takeaway from that is, again, that model-based RL might not substantially improve performance if there's a large distribution shift, if, again, its components are themselves not generalizing. Okay, so what did we learn in this project? First, that model-based pre-training and fine-tuning can substantially improve transfer performance, especially in procedural settings where there's minimal distribution shift, like Crafter. And second, that effective transfer is supported both by having a good policy and a good model. As I discussed earlier in the talk, this is again a confirmation that it's not just enough to have a good model to achieve good generalization and transfer. So coming back to the outline, let me give a quick summary of everything that we've discussed. In the first project, we investigated the role that planning plays in driving the performance of model-based agents. In the second project, we investigated how we can improve the generalization performance by training on procedural environments and leveraging self-supervision. And finally, in the third project, we investigated whether model-based learning can improve transfer performance as well, and which components of the model-based agent contribute to this performance. Looking across these three projects, I think there's a few important things to take away. First, as we found in the first project, planning is most useful during learning by providing a more powerful learning signal and by improving the data distribution to learn from. In some cases, like in Go, it can be useful for decision-making in the moment, but it's not really a guarantee. And many of the common environments that we use in RL don't seem to benefit from it. Second, effective model-based RL relies on more than having a good model. I've said this a million times now. It also requires having a good policy and a value function. And we can improve the performance of these components through self-supervision, though the overall generalization performance will still depend on the generalization capabilities of the individual components. So, self-supervision might help with in-distribution generalization, but we still haven't solved the out-of-distribution generalization problem. In other words, model-based RL isn't a silver bullet for generalization. And finally, as discussed in the second project, self-supervision can bring huge benefits, but not always in the single task setting. We should therefore be really wary about drawing conclusions about an agent's generality from single task RL. Okay, so just in the last couple minutes, I want to talk very briefly about what I think is missing, what things to work on next, I guess. If we revisit some of our intuitions regarding model-based reasoning in light of the results that I've presented, I think that there's really two big areas where current model-based methods seem to fall short. First is this intuition that model-based reasoning ought to confer some degree of deliberative reasoning, or careful, precise, and sophisticated look ahead, as they phrased it in the mu0 paper. And indeed, in some settings, Go being one of them, planning does seem to provide this function. But in many other settings, we found that planning doesn't really help above and beyond the policy prior. We don't need to plan very deeply even in difficult puzzle games like Sokoban. And I think that there's two reasons for this. First, our model-based systems apply planning at the wrong level of abstraction. We plan over these teeny tiny time steps, individual frames, which can make solving problems much more difficult than they actually need to be. For example, we could consider a very simple traveling salesman problem like this one, but that's embedded in a continuous control environment. So with our current model-based methods, we would plan over individual movements of the agent, but that's kind of a silly way to solve this problem. We should use a TSP solver, solve the TSP, and then direct the agent to the individual goal locations. That's a much more efficient and sensible way of solving that problem. And this also then reveals the second way in which our approaches are limited, is that we focus too much on forward planning using generic planners like MCTS. I mean, maybe MCTS would be okay in solving a TSP with 5 variables, but there's much more complicated problems that exist in the world, and we have good solvers for them. We should use them. We shouldn't just be always relying on these very simple generic forward planners. So I think by being able to identify the right level of abstraction and then apply the right solver to the variables that are pulled out in that way will really get us towards this vision of being able to use planning as deliberative reasoning. The other thing that I think is still missing from our model-based systems is generalization, and in particular, strong generalization. As I discussed in the talk, I've shown some improvements to in-distribution generalization, but I wouldn't say that we've made any progress pretty much on strong generalization, where the agent can behave appropriately under radically different conditions. And for this, I think we need 3 ingredients. The first being a generic world model trained on lots and lots of data, lots and lots of experiences across many, many different scenarios. And that gives the agent, the world knowledge it needs to know how to interact with sort of arbitrary settings. Second, I think we need a generic exploration policy that's kind of similar to the world model, but that knows how to generically explore things. If you come into a new room and you're trying to figure out, say, how to use a new presentation system, you kind of have a sense of what things to try and what buttons to press. And that's, that is encoded in the sort of generic notion of exploration of how to explore the world. The third thing is a reward function synthesizer, which I think is basically synthesizing a reward function from natural language. So as humans, again, we don't come into a scenario and have 0 idea about what we're supposed to be doing. We're often given a little bit of context, like figure out how to get your slides on the screen, or do this psychology experiment, or help me solve this problem that my phone is having, etc. Right? I mean, we might not have the task fully specified, but we have some idea of it. And so I think if we had something that could go from natural language to an estimate of where the rewards are, would then be the third component that allows us to basically train an agent in its imagination using generic exploration with the estimated rewards and really rapidly come online as something that can generalize strongly to new scenarios. And I think when combined additionally with better abstractions and reasoning mechanisms, like I talked about on the previous slide, I think we might actually have a chance to make headway on long horizon sparse reward tasks too, and really start seeing, very capable general agents. So that's just a few thoughts on what I think is missing and what is interesting to work on next. And I would love to discuss further during the questions. Just to wrap up, I want to thank my co-authors. You can find the citations to the papers that I talked about here. Thank you very much for your attention and happy to take questions.
So please go ahead. People online, you can text your questions and we will read it out loud. So anybody here? Some question to start? Okay.
In the model architecture, you had the self-supervision component to it. And on the diagram, you had these things called dynamic heads, and they seem to be predicting T plus I or T plus K. Are they different networks for each different I that you have, or is it the same network and you feed it in the time step that you're actually trying to predict?
Here, you mean? Yeah, the dynamics heads are the same. So it's one observation encoder, one network for the prior heads, one network for the model, and one network for the dynamics, and then it's unrolled over time.
So the same model uses the same head to predict T plus I. Okay.
Yep.
Are you feeding in I, or is it just?
No, it's like a recurrent. It's a recurrent architecture. Yeah.
How do you feel about using LLMs as your generic world model?
Well, I mean, so there are, I think, good aspects to it and also bad aspects to it. I don't think LLMs capture enough of like the actual world knowledge that are necessary. I think the way I like to think about LLMs is they're a really good prior on the space of world models. They know a lot about what things go together and what things might be paired together, what things could happen, but they just make stuff up, right? They're not actually a world model. They don't follow any real rules and dynamics. I think, they're also not grounded. So they, especially if you're considering say like a robotics setting, I'm not sure how useful they would be as like a world model on their own. Though maybe when paired with something like a video model, they might capture some more of that type of information. I do think where they come in handy is in terms of providing some amount of abstraction or like breaking the problem down into parts. People are just starting to work on this and it seems like they can do it to some extent, maybe not in a super sophisticated way yet, but maybe that'll come. So I would say I wouldn't use them as a world model. That's not how I would view them. I would view them more as a way of generating hypotheses about how the world might be carved up into parts. And then you can do sort of typical model learning stuff on top of that. Yep.
In your talk, you've been talking quite a lot about the link between the performance of your world model, of your world predictor, the planner, and the performance of the agent policy. I wonder, have you been able to establish a link between, like a curve thing, between the performance of your world predictor and the performance of your agent when it comes to generalizability? I'm interested in this, particularly in a context where you're not on policy, but off policy. Now you have a world model that you know the performance of it, but you cannot improve it anymore. Can this tell you anything about how well your agent will generalize?
Well, I suppose, tell me if this answers your question, but I think in the first part of the talk, we sort of were looking at that because we were looking at, go back to, yeah, maybe this slide. So like here, this is effectively looking at two different qualities of the world model, right? One that's world learned and one that's a perfect one. So this on the model that's being used in this plot can't improve any further because it is the true model. And it certainly does improve the generalization performance, but only up to a degree. So, I mean, we haven't necessarily created a plot where say on the x-axis is quality of model and the y-axis is generalization performance. That could be a cool experiment to do. I would expect that you see the quality of the model clearly does help to improve generalization, but probably only in distribution generalization and only up to a particular only up to an extent. I think you would still ultimately be limited by the other components. Does that answer your question?
Yeah. Thank you.
In the contrastive loss, you compare a later frame to a previous one? Or
So
another previous?
So the contrastive loss is really similar to the SPR loss. Sorry. So basically the SPR loss predicts the embedding at time t plus k, and what the contrastive loss does is instead of just predicting that embedding, it does a classification on whether that embedding matches the actual embedding produced by the true observation.
There a need to balance between the SPR losses and the mu0 losses? As in, like, how did you consider the weightings between the two when updating, for example, the entire model?
Yeah, good question. If I remember correctly, I don't think that we had to do much fiddling there. I think we just added the loss and it seemed to help. The one actually nuance which I didn't talk about that we did, which was actually with the reconstruction loss, not the SPR loss, is we added a max error loss to, so it wasn't like a pure L2 reconstruction loss. We additionally said basically we added a term for the pixel with the highest error. So that sort of forces it to, you know, do well on all of the pixels, not just the average pixel. Does that make sense? That seemed to actually help quite a lot to add that term there. But in terms of the other losses, I don't think we had to do very much in terms of like looking at different weightings or fiddling with the hyperparameters too much.
So I was curious about the rationale behind research, just Monte Carlo research for action selection, in which you would need to account for exploration at research level, such as with the UCT. And because I think the real action is only possible from simulated ones. So with the university, you would have to sample a sufficiently representative action space. But in contrast, why don't you use research for evaluating a state, such as a backup target for the value function, like a huge Bellman optimality backup targets?
So we actually do that. So the value targets are nstrap bootstrap returns, where each of the rewards at the times t plus n are using the environment rewards, and then the bootstrap value is the one that comes from MCTS.
Your real action is from Monte Carlo research instead of like a after critique.
I guess I'm not totally sure I understand the question. So the action is the one that we execute in the world. So the search gives us both the action that we execute and that's the one that we, is that?
The real action that you take in the real world is from Monte Carlo research.
Yeah.
But that means you are sampling a subspace of the action space, and you are evaluating this subspace, and you can only choose one from the sampled actions as the real action.
Oh, I see. Yeah. So I think in practice, that's a great question. Sorry, I didn't understand the question initially. So in practice, you would choose the search budget that's high enough such that you would expect it to sample all of the actions at the root. So you don't have to worry about that issue. That actually, this paper that I mentioned somewhere. I don't know where it is now, but the paper that I mentioned that has to do with like adding this loss back to the like using the planner loss onto the policy. We explored that, and we actually we were sort of exploring with a slightly different version of, it wasn't mu0, it was because it was a value-based agent as opposed to a policy-based agent. And there, like, we get updated Q values from the MCTS as opposed to updated policies and state values from MCTS. And that allows us to actually get more information about all of the actions, not just the ones that are explored during search. And then you can use that in your update. And that seems to also work quite well, but and especially in cases where you have a low search budget, that works much better than what mu0 uses, exactly for this reason, because it doesn't sample enough of the actions at the root. Yeah, and in practice, because these state spaces are, the action spaces are relatively small, like it's usually like, 10 to 20 actions, then 50 simulations is the typical amount, is fine. That's another reason why you actually have to have a lot more simulations for Go too, because Go has a lot more actions than the other environments.
For large action space or continuous action space, do you think that using tree search to inform the value function is actually more beneficial than using to inform directly the policy?
I think it does need it for both, but it just then you have to have a larger budget to account for like not being able to explore enough. But I think, yeah, I think just using it for the value function isn't, or the state value function at least, isn't enough. Like you really do need to have it anchoring onto like what the planner is doing too. Yeah, I think there's probably more like you could explore there in terms of some of these questions. We haven't like fully explored that space of possibilities. But yeah, my intuition at least would be that you still need the tree search. You just like, basically the requirement is you have to do enough of it. Yeah.
Okay, so very last question very quickly from audience online, from Andrew. In what scenarios do you prefer V0 and CTS over Dreamer dynamics?
Mhm.
And in what situation do you prefer Dreamer again?
Well, I think the question is like, when would you use mu0 versus when would you use Dreamer? So good question. I think that they are actually somewhat complementary approaches. So Dreamer is a Dyna style algorithm where it learns the world model and then it uses the world model to train the policy. Whereas mu0 is kind of, well, it does a bit of both. It uses like, tree search to help train the policy, and then also the model, and then it uses the model to improve the tree search. I think that like Dreamer isn't able to sort of like benefit from this idea of using the planner as like this expert that improves upon the existing policy. But I think you certainly could do that in a Dreamer style approach too. Not even necessarily to generate actions at test time, but in the policy learning phase, like rather than just say, generating random data, you could actually say, okay, here's my state, I'm going to plan from this state, and then, use the results of that plan to update the policy in a more model-based way. So not just relying on the model for data, but relying on it also for generating targets. And similarly, actually in mu0, there's a variant of mu0 called mu0 reanalyze, which does a lot more replay. It kind of is much closer to a Dyna style algorithm where it keeps a replay buffer of states that it's encountered, and then it replays from those states and then uses the model at the planner to reevaluate those states and again generate better learning targets. So I think, and that is like way more data efficient than the original version of mu0. That seems to be Dreamer's like biggest like benefit, is that it's super data efficient. But I think you could basically combine the best of both. Is like you can get both the data efficiency and the improved learning signal. So.
Okay, so I think we can close it now. Thank you those who came online.